Okay, so today's video is going to go through pages 7 through 10 of your packet. If you have not picked up a packet yet, this is the part where you really kind of need one because this stuff is really hard to write in by hand. So we're going to go through the notes and then I'm going to talk about graphing by hand as well. So, polynomial functions. So the definition here on this page of polynomial functions is really technically mathematical. So they talk about a polynomial function in the form a n x to the n, etc., and it's really long and complicated. Okay, and it says coefficients are real numbers, a and the n cannot be 0, and n is a positive integer. Basically what this gets into is the fact that for something to be considered a polynomial function, you cannot have any negative exponents. You also cannot have any variables in the denominator like we talked about before. So that's kind of where they're going with this. So a to the n, or I'm sorry, a sub n is what it is how you say that. But basically they're calling that the leading coefficients. Essentially, when we talk about leading coefficient and leading term, let me change colors because white on white does not work. Your leading term is the term with the highest exponent. So we'll go through some examples here in a little bit. But when we talk about leading term, it's the term with the highest exponent. That term also, remember, tells you the degree of the polynomial. Not all polynomials are given to you in standard form. So remember, standard form starts with the highest exponent and works its way down. So it is a good idea to put your polynomial in standard form before you start working with it, because this will allow you to actually see what is the leading term, what is the degree, what is the leading coefficient. Okay, so here are some examples. So it says classify each polynomial function by degree and give its leading coefficient. So we're just going to list the degree as a number, but we can also write in the names as we go through this. So f of x equals 4. We have just a number, no letters, but it's still a polynomial of degree 0. Okay, so this is called a constant function. And a constant function will have no variables, so no letters at all. The leading coefficient here is just that number 4. And coefficient means number in front of the variable for that particular term. All right, now let's look at the second one. Our highest exponent is 1, so it's a first degree, which is also called linear. The leading coefficient here is -5. Coefficients never include variables, it's always just letters. Okay, the next one has degree 2 because x squared is your highest term, so it's quadratic. And your leading coefficient is 12. Let me move my page up a little bit. The next one is cubic because it's degree 3. The leading coefficient is -1. The next one is quartic, which is degree 4. Leading coefficient is -3. And the final one is quintic because it's degree 5. And I'm going to write that over there. And a leading coefficient of +9. So all of these functions were given to you in standard form, and we use that to determine the degree and the leading coefficient. Okay, so parent functions, if y'all remember from what we've done to this point, are those basic functions that give us the idea of the shape of similar functions. So for example, constant functions always form a horizontal line. And just depending on the value of c, which c is just a number, okay? It could be any number we want. That's going to determine where your constant is. So if you have f of x equals 1, you would have a horizontal line at 1. If you have f of x equals -5, you'd have a horizontal line at -5 and so on. But constant function is always a horizontal line. Okay? For linear, this is a first degree. So your parent function is f of x equals x. And that's going to form a diagonal line. On the parent function, it goes through 0, 0, and has a slope of 1. Quadratic we worked with, this forms that parabola shape, f of x equals x squared, centered at 0, 0, opening up. Now a cubic function is degree 3, and it kind of wiggles, is what we call this, as it goes through 0, 0. So it kind of scoots around. It's going down on the left and up on the right. Okay. And then we come to the next set of functions, a little bit higher degree. Quartic functions, x to the 4th. The parent function looks like kind of a wider parabola. It's still centered at 0, 0. These guys can get really weird. They can do some really weird stuff. So one thing about the parent functions for these higher degree polynomials is they kind of give you a general idea, but when we get into cubic, quartic, and quintic functions, we can't really use transformations to graph those as easily as we could, say, quadratics. So these can get a little strange the more complicated they get. And then a quintic function, x to the 5th, would be the parent function. And it kind of looks like the cubic function. It wiggles through 0, 0, but it's a little bit skinnier. Okay. So, in behavior, this describes what is happening on the ends of the function. Where is it going on the left and the right? So, I have written the notes through here. But basically, in behavior, describes kind of where the arrow is pointing at the end of the functions on the left or right side. As x approaches infinity, that's the right side of the function because that's x is getting more positive. As x approaches negative infinity, refers to the left side of the function. So on this assignment, everything is right first and then left. On your delta math, I believe it is the same way, but just pay attention. X approaching positive infinity is the right. X approaching negative infinity is the left. And in math, that arrow means approaching. So what I'm going to do is I'm going to pull open a Desmos and I'm going to graph a few of these just to kind of show you what a general idea of how we're describing it and how I got these answers. All right, so my first function is f of x equals 4x to the 4th plus 6x to the 3rd minus x. Okay? And on Desmos, you don't have to enter the f of x equals every time. There's some reasons why you should, but in the interest of speed, I'm not going to do that today. So, let me build that up a little bit. So here's what you can see. Here's the graph of this function. And if I zoom out, all that's happening is that's getting bigger. But you can see that this thing is like crazy, right? So what we're looking at, though, is the end behavior. Where are these ends pointing? So if I draw little arrows at the ends, on the right side, and this is the right, and this over here is the left. On the right side, our y values, or f of x value, is approaching positive infinity. So it's going up, okay? So positive infinity means up. On the left side, f of x is also approaching positive infinity, or going up. So both ends are pointing up, okay? Let's look at another one. So on this next one, we have f of x equals negative x squared, and then plus x. So this graph, if I look at it, here's where my ends are going. they are both moving down. So here's the left side, here's the right side. So on both of these, f of x is approaching negative infinity, and f of x is approaching negative infinity. They're both moving down. We're getting more negative. Okay. So, like I said, these answers are already on here, but I kind of wanted to explain to you guys how we got these, and it's really looking at where the arrows are pointing. So let's look at another one. We have f of x equals 2x to the third. Okay, so this time, if you notice, your arrows are pointing in opposite direction. So on Desmos, they don't give you the arrows, but you can kind of imagine they're there. This arrow, this is the right side. So on the right side, f of x is pointing up. On the left end, f of x is pointing down. So right up, we call it towards positive infinity. Left is moving down, so we say that's towards negative infinity. So basically, that's what I did on 4 through 6. So what I want you guys to do is to graph those functions and see if you can figure out how I got those answers. How do you represent up versus down? How do you figure out which is the right side and which is the left side? Okay. I also summarized this for you guys. Let's see if I can get rid of this window real quick. Apparently not. Okay. So I also summarized. Okay, so I also summarized here at the bottom the pattern. How you can tell which way the ends are pointing based on both the degree and the leading coefficient. So when we talk about even degree, that means that your degree would be 2, 4, 6, etc. So if your degree, your highest exponent is an even number. If your highest exponent is an even degree with a positive leading coefficient, both your ends are going to be pointing up. So that would be like example, if I scroll up a little bit, that would be like example 1, okay? If you have an even degree and a negative leading coefficient, it's going to be like examples 2 and 5 with both ends pointing down. Odd degree would be degrees of 1, 3, 5, or 7, etc. If it's odd and positive coefficient, then I didn't do the best job of drawing here. Your left end will be pointing down and your right end will be pointing up. If it's odd degree with a negative leading coefficient, the left end points up and the right end points down. So on 7 and 8, we're kind of summarizing that idea. On 7, both ends are pointing down, so it's going to be even degree since they're both pointing the same direction, and a negative leading coefficient. On number 8, the left is going down and the right is going up, so it's going to be odd degree since they're going in opposite directions, and that would have a positive leading coefficient. Okay. Turning points, relative maximum, relative minimum. And then we're also going to talk about increasing and decreasing intervals. So, I'm not going to get into today all of this stuff here at the bottom with the graphing. I'll tell you guys what I want you to do there. But you do need to know what these terms mean for your Delta Math assignment. So, when we talk about turning points, these are points where the function switches directions. If you look at like this little graph here, like this is a turning point, this is a turning point. If you trace along as you move from left to right on the function, you can see that it go up here, and then you turn and you start going down, and then you turn and you start going up again. turning points can be classified as either a relative minimum or relative maximum, depending on if they're the highest point in the region or the lowest point in the region. So relative maximums, we sometimes call it relative max, are top points. So what we could call hills. If you think about if you're riding a roller coaster, relative maximums would be like the top of your hill. Okay? Relative minimums are your valleys. They're the little scooped out points that are lower than everybody else in the area. So if we graph this function in Desmos, we can actually find the values of the relative minimum and the relative maximums. Okay? We'll talk about increasing and decreasing intervals when we come back, hopefully, or on the 19th, so the Tuesday after Martin Luther King Day. So I'm not going to get into increasing and decreasing intervals today too much, except to kind of understand the basics of what they are. Okay? When we talk about increasing intervals, those are the x values where the function is rising. So, if I bring back my Desmos window and I graph this function, x to the third minus 6x squared plus 7x plus 2. Okay? So this is the same function I have on the front page. If I think about increasing, I'm always starting at the left side of the function. And an increasing interval is where when you start from the left and you're going uphill. So this area here is increasing. All the way up until this point. Okay? Then from here to here, this interval is decreasing. And then when we come back here and we start increasing again. And you can kind of think about it, like I said, if you're on a roller coaster and you're riding in the car, increasing is going up, then you come down, and then you go back up again. Your assignment tomorrow will just be to look at a drawing and label different points. So you actually have 2 drawings to do. You're going to have to show which ones are increasing, which ones are decreasing, where are your turning points. What is your end behavior? So this is going to be kind of a summary drawing. So we will get into on Tuesday the 19th, we'll get into how to determine those increasing intervals with the numbers that I came up with at the bottom of this page. And we'll actually graph the problems on Tuesday. So we're not going to worry about that today. So all you need to worry about for today, taking the notes, which most of them are filled in, so just kind of add in some high points. Really making sure you study the definition, and then work on the January 14th assignment on Delta Math. So relatively easy day. Email me if you have questions or concerns. And then tomorrow, like I said, you just have a small summary Google Doc. It should be pretty quick. And then if you get everything done, you can use that time to catch up.